All right, so now we move on to section 7b, which is a more practice on probability problems. And here we specifically focus on what's called independent events versus dependent events. So the definition of an independent event is if you have two events that are independent, we only have this if the outcome of one event does not affect the probability of the other event. For example, rolling dice. If you roll a dice twice, the outcome of the first roll does not affect the outcome of the second roll. So say you have a 6-sided dice. If you roll it once and it lands on a 2, if you roll it a second time, you still have the same chance that it lands on a 2 or a 3 or a 6, right? Every time you roll the dice is independent from the other time that you roll the dice. So think of another example. So another example, of course, probably the most common example of independent events would be flipping a coin. Right? Because if you flip a coin, you only have two options, heads or tails. And every time you flip the coin, you still have the same chance of getting a head or a tail. Right? Each event does not affect the following event. Now we talk about calculating and the probabilities for independent events. So, if A and B are independent events with probabilities, probability of A and probability of B respectively, then we can calculate the probability that A and B both occur using this formula. So it's very straightforward. In fact, we use this in section 7a. Really, all this is saying is when each event is independent, we just take the probability of the first event happening and we take the probability of the second event happening, and then we multiply those two. Now, note that this principle can be extended to any number of independent events. So if you have 3 things happening, 5 things happening, you would just have the 5 probabilities and you would multiply them all. Now it says, consider the 36 equally likely outcomes that result in rolling 2 dice. Okay, so I actually made a bigger one here for you guys to see. So here, right, you have the 6 different ways that one dice could land, and then the same 6 ways that the other one. Okay, these right here give you the sum, right? So if they both land on 1, you get a 2, right? If this is a 1 and this is a 2, then you get a 3, and so on. Okay, which is pretty much what this is here. It's just showing you as an ordered pair. So if you want the sum, you would add them. If you want the product, you would multiply them. If you want the difference, you would subtract them. And of course, if you want the quotient, you would divide them. Now, typically, we only really ask questions about sum and maybe product, but they're numbers, so you could do any of the 4 operations. So it says, use the diagram to find the probability that both of the die land on 5. So if you look here, right, how many ways can both of the dice land on 5? Only one way, 5 and 5. We cannot switch them because it's the same number. So here's only one way. Right, one probability. So we have, right, like we talk about on the top goes the question, so there's only one outcome, and on the bottom goes how many total outcomes, which is 36. Okay, this is one way of finding the probability. Now let's find the probability using this formula. Okay, so calculate the same answer given the formula. Probability of a 5 and a 5. So how do you find that? Well, you find the probability that when you roll the dice, you get a 5 the first time, and then the second time you also get that 5. And so what is the probability of just the one dice landing on a 5? Well, you have one option out of 6. So the probability is 1 out of 6 for just this event. Now, this event has nothing to do with this event because you're rolling the dice again. So again, you have a probability of 1 over 6. And our two probabilities get multiplied. Now remember, when you multiply fractions, you do not need the common denominator. All you do is multiply directly across. So 1 times 1 is 1, and 6 times 6 is 36. And there you go. So very commonly people use this formula whenever they get a lot of events, right? So 2, 3, 4, 5 may be easier to do it this way than to think about all the total outcomes like here. Okay, but either way still gives you the same results. All right, let's look at another example. Consider the 8 equally likely gender order combinations for a family with 3 children. And so this we had talked about in 7a as well. We had listed all the different ways, right? So 3 girls, first 2 girls, and then a boy, boy, girl, 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 boy, 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 girl, boy, boy, girl, and then all 3 boys. Using the list above, what is the probability that all 3 children are girls? So when you have a list of all the probabilities, then we can directly get our answer because we know the total. There are 8 likely outcomes, and it's asking us for the probability of all 3 girls, which is the 3G, which is only 1. So 1 out of 8, and you're done, right? But what if you don't have this list, right? Just like here. What if you don't have the list ready available? Well, then using the formula would be a lot easier to do it. So calculate the same answer using our formula. So these are all independent events, right? If you have a girl with the first child, the second time that you have a child, it could, again, the same likelihood of getting a girl or a boy. And so here you have the probability of first child is a girl. So here, how many options are we considering for this scenario? Just 2, boy or girl. So you have 2 on the bottom, and then there's only 1 possibility of a girl. Now, when you have the second, it's the same thing, 1 out of 2. And then again, 1 out of 2. So to find the probability that all 3 are girls, we just multiply. So remember, multiply across. 1 times 1 times 1 is 1. 2 times 2 is 4, and 4 times 2 is 8. Now, a common mistake people make is they add the probabilities. So please don't make that mistake. We always multiply the probabilities of independent events. Okay, when they don't affect each other, we find each individual probability, and then we multiply. So you see how we get the same answer? So if you have a list of all the combinations, you can directly get your answer from here. But if you don't have a list and you don't want to create a tree diagram or create a list, you can just do it by using this formula. All right, let's continue. All right, match versus no match game. So the game described below are designed for 2 players. Each pair of players will need a paper bag containing 2 blue tiles and 2 yellow tiles. So I here have the 2 yellow tiles and the 2 blue tiles. Now play each game as described below and then answer the questions below. So since I have to play by myself, instead of using a bag which may be see-through, I'm going to use this little teacup. And I'm going to put those in there. Okay, so the first game is drawing tiles without replacement. So place 2 blue tiles and 2 yellow tiles in the bag. Okay, so that's done. Shake the cup, in this case. Player 1 draws 1 tile from the bag and places it on the table. Then player 2 draws 1 tile and places it on the table. If the tiles match, player 1 gets a point. If the tiles do not match, player 2 gets a point. Play 20 rounds and record the results on the chart below. All right, so I'm not going to look. This is now going to be player 1. All right, so we got 1 yellow. Okay, so places it on the table. Player 2 draws now. These are hard to pick up. And I got a blue. All right. tiles match, player 1 gets a point. If the tiles do not match, player 2 gets a point. So here, player 2 gets a point. All right, let's put them back in and go again. We're going to go 20 rounds. So shake it. All right. All right, first is blue. So first player, second player. All right, they don't match. So again, player 2 gets the point. All right, just hard to do. All right, so the first player is yellow. Second player is blue. So again, do not match. All right. Oops, I picked up 2 at one time, so I gotta do it again. So, blue. That was again. Yellow. It's kind of hard playing by yourself, but. Okay. Blue. Yellow. Whoa, a lot of times they're not matching. Blue, yellow, don't match again. This is hard to pick up. Blue and yellow. Yellow, blue. Looks like we can't get any matching. Let's try again. Yellow and blue. Make sure these are blue. Blue. All right, first time. So that's 10. We're going to play 10 more times. Yellow, blue. Picked up 2 at one time, so try it again. It's hard to even grab these. So blue and blue. All right, so twice. Blue. And yellow. Clearly it would have been funner if there were 2 of us playing this game, but you get the idea. So blue and yellow, so they don't match. Yellow and blue, so they don't match. Let's do blue and yellow. They don't match. Yellow and yellow. All right, so those match. 3 more times. Blue. It's hard to even get these. Oh, blue again. 2 more times. Blue. And blue. Okay, so that's 6, 15. So 1 more time. yellow. So they don't match. Whew, alrighty. So of course, if you want, you can play this game with a family friend or your family, if you have someone there living with you, and then see what kind of a tally system that you get, right? And so here we have 6 points here, and then 14 points here. So what is the percent of games won by each player? Well, how many games did we play? 20. So this is, the percent will be 6 out of 20, okay, which can be simplified by 2, so 3 out of 10, okay? And then this one will be 14 out of 20, which can be simplified by 7 over 10. So this will give us, what, 30%, and this will give us 70%. So based on your experience of playing this game, does the game seem fair or not fair? Okay, so even if you don't get these exact values when you're playing, you should get a not fair outcome. So in this case, player number 2 won a lot more than player number 1. Okay, so it doesn't seem fair, because if it should be fair, they should win more or less the same number of times. In this game, the first tile is not returned to the bag before the second tile is drawn. We say the tiles are drawn without replacement, because I took one from the cup and I put it down here, and then I selected my second. How is the second player's turn affected by not replacing the first tile? Okay, so why this makes a difference is, we could say the number of blue and yellow tiles are no longer the same, making the probability in favor of player number 2. Okay, because if I selected a blue first, well, when I select my second tile, if I want player 1 to get a point, it has to match. But what's going to be left in here? You're going to have 2 yellow and only 1 blue. So the chance of getting a blue the second time here will be 1 out of 3. It's no longer 2 out of 4 or 1/2. So you have a player 1 getting a smaller likelihood of winning the game, and player 2 getting a much higher chance. So now let's look at the game if we draw the tiles with replacement. So place the 2 tiles, the blue, 2 blues and 2 yellows in the bag. Shake the bag. Player 1 draws 1 tile from the bag, records the color, and turns the tile to the bag. Then player 2 draws 1 tile. If the tiles match, player 1 gets a point. If they do not match, player 2. And then again, it says to play those rounds. All right, so let's do this. All right, so I got a blue, and then I'm going to put it back in here. And let's see what I get. I got a blue again. All right, so player 1 wins. Got a blue. And I got a yellow. They don't match. All right, I got a blue. Put it back in. Got a blue again. Got a yellow. And then I got a blue. Got a yellow. Then I got a blue. Got a blue. Got a blue. Got a yellow. Got a blue. Got a blue. Got a yellow. Got a yellow. Got a yellow. Oops, flew up. Got a blue. Oops, put it back in. Got a blue again. Got a blue. Got a yellow. Got a blue. Got a blue again. Got a yellow. Got a blue. Got a blue. Got a yellow. Got a blue. Got a yellow. Got a yellow. Got a blue. Got a blue. Got a yellow. Got a blue. Got a yellow. Got a blue. Got a blue. 5, 10, 15. So one more time. So I got a blue. And I got a yellow. Well, that one was kind of crooked, so let's do that one again. So it's fair. So I picked this first, so blue. And blue. Alright, so we got 8 and 12. So this would be 8 out of 20, games won. We can divide this by 4, so that will give us 2 out of 5, which is 40%. And then 12 out of 20 can divide by 4 as well, and that gives you 3 out of 5, which is 60%. So here, they're not exactly equal, but it is definitely closer than the previous. And of course, this goes back to the law of large numbers. We only play 20 times. Now, if we were to play 500 times or 1,000 times, we should definitely see this become more equal. So here it says, does this seem fair? Why or why not? And so here you may say, well, it's still not fair because these, you know, this is 40% is quite a bit lower than 60%, but the percentages are closer. So this can kind of depend on what you're saying here. Because we are putting back a tile, we technically, theoretically, have that same chance of a red or a blue being picked a second time. Okay, so we could say something like player number 2 technically won a few more times than player 1, but the percentages are closer. So again, answers will vary. So if you do play this game on your own, then you can see what it ends up happening for you. All right, so now we talk about the calculation of theoretical probability, right? So what we just finished doing by playing the game, we did relative frequency or empirical probability because we actually did the experiment and we recorded the data. In theoretical probability, we don't do any of that. We just apply the rule. So on page 1, we verified the following rule for calculating and probabilities involving the two events, right? So we verified that this still gives us the same answer as long as the events are independent. Now, we can extend this rule to apply to dependent events as follows. So dependent events and the multiplication principle. For two dependent events, A and B, we calculate the probability that event A occurs and then event B occurs by using the multiplication principle as follows. So we have the probability of A and B is going to be the probability of A multiplied by the probability of B given A, where probability B given A means the probability that the event B occurs given that A occurred. So now let's look at game 1. Drawing tiles without replacement. In game 1, the first tile is not replaced before the second tile is drawn. The act of not replacing the first tile changes the tiles which are available for the second draw, which means that the outcome of the first draw affects the outcome of the second draw. Okay, which means that these are dependent events. So drawing two tiles in a row without replacement would be dependent. Okay, so whenever it's without replacement, which means you're not replacing what you got in the first outcome, it's always going to be dependent. If you replace it, then it becomes independent. So calculating the probability of each possible outcome in game 1. Okay, so here is a tree diagram. So as we did in 7a, a tree diagram is very helpful visually to understand what's happening, because sometimes people get very confused with probability. Even though there's no big formulas, people just get confused. And so by drawing a tree diagram, that can really help you see what's going on. So this is the bag, right? You have two blues and you have two yellows. So the first time you draw, you have two options. You can either get a blue or you can get a yellow, right? And then the second time you draw, if say you drew a blue first, now you have two options. You can draw a blue again, or you can draw a yellow. If in the first draw you first drew a yellow, then still you have two options. You could draw a blue in the second turn, or you could draw a yellow in the second turn. Okay, now let's calculate the probability. So let's look at the probability of our first draw. What is the probability of drawing a blue? Well, how many options do we have here? We have 4. And how many are blue? We have 2. So our probability is 2 out of 4, or 1/2. Now, what about for the yellow? Well, it's the same because we still have 4 options in our first draw, and 2 of them are yellow. Now, let's look at the second draw. So what happens if you draw a blue first? Now, when you do the second draw, how many are left inside since we did not replace? Only 3. So now our denominator changes to 3. Now, how many are left with blue? Well, we already used 1 blue, which means you only have 1 out of the 3 that are left. You see? So the probabilities are not equal anymore. Now look here. Here would be the same idea. Here you drew a blue, okay? So what is the probability of getting a yellow on the second? Well, let's see. If we don't have a blue, we still have 3, but how many of these are yellow? 2 are yellow, you see? So now in the second draw, the chance or the probability of drawing a yellow is much higher than drawing a blue. So to find the probability of then getting 2 blues, we just follow that arrow. So we have a 2 out of 4 chance of the first, and we have a 1/3 chance of the second. And remember, we multiply. So 2 times 1 is 2. 4 times 3 is 12, and this gets simplified to 1/6. Okay? So you have a 1/6 chance of rolling 2 blues, or I'm sorry, selecting 2 blues. All right, let's look at this one. So here, this would be the probability of drawing a blue, and then the probability of drawing a yellow after you've drawn the blue. So we have our 2/4 times 2/3. Now, 2 times 2 is 4, and 4 times 3 is 12. Now, if we simplify 4/12, we get 1/3. Okay, so a much higher chance, 33%, compared to 1/6, which is half of that. All right, now what if we pick the yellow one first? Now let's see here. Here we would still only have 3 left, right? Because now a yellow is gone. But how many blues are left over for us to select? We have 2 out of the 3 to select. Now what about the yellow? Well, we're still going to have 3. Now we selected 1 yellow in the first selection. So now how many yellows do we have to select out of the 3 that are left? Only 1. So the probability of selecting a yellow first and then a blue is going to be this and this. So 2/4 times 2/3. So again, we get 4/12, which is 1/3. Now, what is the probability of getting those 2 yellows? So the first one, you have 2/4 times 1/3. So 2 times 1 is 2. 4 times 3 is 12, and then again we simplify to 1/6. Okay? So this is your tree diagram, and then this is how you can find the probability of each of those 4 outcomes. All right, so here essentially we're continuing the game with the answers already listed here, just so that way we don't have to keep flipping back and forth on our page. And so it says, recall that player 1 wins if both tiles match. So when do they both match? They both match here, and they both match here. Okay? Now, there are 2 ways for the tiles to match, right? Blue, blue, yellow, yellow. These events are considered non-overlapping events because the game can result in blue, blue, or yellow, yellow. But the game cannot simultaneously result in blue, blue, and yellow, yellow at the same time, right? They're impossible for them to happen at the same time. So we call them non-overlapping events. Now, for 2 non-overlapping events, we calculate the probability that either A or B occurs by adding the 2 probabilities together. Okay? So, player 1 wins the game if the tiles match, which means blue, blue, or yellow, yellow. Use the probabilities that we just calculated here to find the theoretical probability that player 1 wins game 1. All right, so our chance of getting 2 blues was 1/6. And then our chance of getting 2 yellows was also 1/6. Now remember, when you add fractions, you add the numerator, so 1 plus 1 is 2, and you keep the denominator. And then we always simplify, so we end up with 1/3. Okay? Now, what is player 2 wins the game if the tiles do not match? And they can be mismatched in 2 ways. You could have a blue and then a yellow, or you could have a yellow and then a blue. Use the idea of non-overlapping events to calculate the theoretical probability that player 2 wins game 1. So, the probability that player 2 wins means we can have the probability of it being blue, yellow, or yellow, blue. Now, what is the probability of us getting the blue, yellow? So if we look back here, that was 1/3. And the probability of getting yellow, blue was also 1/3. So this is now 1/3. And this is 1/3. Now, if we add them together, we get 2/3, which cannot be simplified. So that's our answer. Now here, D says, based on the theoretical probabilities calculated above, is game 1 fair? Why or why not? So here, it's very obvious that the game is not fair. Okay, we can say the theoretical probability that player 2 wins the game is twice as high as the probability that player 1 wins. So imagine this. Imagine that a friend said, hey, you want to play this game? Let's put some money down. If you win, then I win the money. And if I win, if you win, you get the money. And if I win, I get the money. Right? Would you want to play a game like this if you were player 1 and they wanted to be player 2? Well, if you don't think about it, right, if you don't think about the fairness behind the game, then you can end up losing way more times than you end up winning, right? And that's really what happens with gambling, right? Because if you think about casinos, they are made to win more, right? The house is made to win more times than the player, okay? And so the probability in a casino is always going to be stacked against you, okay? It's never going to be a fair game in the sense that the house is always going to have a higher chance of winning than you are. Now, does that mean you're never going to win? No, people obviously do win in gambling, but way more people end up in debt or losing a lot of money. Okay, that's why there's that saying, the house always wins. And if you actually use math to help you, right, which is called counting cards, which, is considered cheating in a casino, when in reality, it's just using math to provide you with the best outcome. But of course, they don't like that, and so that's why it's banned in casinos. All right, now so let's do the theoretical probability now with the replacement of the tiles. Okay, so in game 2, the first tile is replaced before drawing the second tile. The act of replacing the first tile restores the bag for the second draw, which means that the outcome of the first draw does not affect the outcome of the second draw. So when you're drawing 2 tiles in a row with replacement, this is an example of independent events. So let's calculate the theoretical probability. So we're going to do the same thing on the tree diagram. So the first time you select a blue, right, you have 2 out of 4. That's my probability. And then the same thing for the y. You have 2 out of the 4. Now the second time you draw, since you replace this back into the bag, how many do you have to choose from? You have 4. And how many are blue? You have 2. You see? And this is why they're independent, because whatever you selected in the first draw does not change the probability of the second draw. Now, if we go this direction, so you selected a blue, you put it back in, when you go to draw a second time, the chance of getting a yellow, you still have 4, and you still have 2 yellows. And that goes exactly the same here. So this is, again, 2 out of 4, and again, 2 out of 4. So, what is our probability of this direction? You see how there's 4? 1, 2, 3, 4, which means there are 4 possible outcomes. And so we just follow each kind of arm in the tree, and we multiply the probabilities to get our outcome. So we have 2, 4 times 2, 4, which of course gives you 4 out of 16, which is 1/4. Of course, if you want to simplify to 1/2, that's fine. So for example, we could do 1/2 times 1/2, and you see, you directly get the 1/4. And it's going to be the same thing here. 2/4 times 2/4, and that gives you 1/4 as simplified. And then again, 2/4 times 2/4, and then that gives you 1 out of 4 also simplified. Okay, so here, do you see how every outcome has the same chance of happening, is equally likely to happen? So, player 1 wins the game if the tiles match. So if we have the 2 blues or the 2 yellows. Use these probabilities. Calculated, I guess this should say 8A, not 7A. So, if player 1 wins, we have the probability of this one or this one. So the probability of the 2 blues is 1/4, and the probability of the 2 yellows is 1/4. And now, because these do not overlap, we just add them together, which gives you 2 out of 4, or 1/2, which means you have a 50% chance. Player 2 wins the game if the tiles do not match. So the tiles can mismatch in 2 ways. So we could have blue-yellow, or we could have yellow-blue. Use the idea of non-overlapping events to calculate the theoretical probability that player 2 wins game 2. All right, so here we have probability that player number 2 wins. And like I said before, this is very important that you write the setup. You don't just want to have 2 fractions with no explanation. So please make sure you do this every time you write an answer to your probability. So then we have the probability. Well, how does the player 2 win? It could be blue-yellow, or it could be yellow-blue. All right. So what is the probability that we get a blue-yellow? 1 out of 4. What is the probability that we get a yellow and a blue? Again, 1 out of 4. So if we add these together, we get 2 out of 4, which equals 1/2. So player 1 and player 2 have an equal likely chance of winning the game if we play with replacement. So does this game seem fair? Yes. Both players have a 50%, which is the half, chance of winning. All right, let's continue. So now let's do some practice questions. So consider the following experiment. Rolling a fair 6-sided dice 3 times in a row. So first of all, is this independent or dependent? So does the previous outcome get affected? Oh, sorry. Does the current outcome get affected by the previous outcome? So for example, if you throw the dice the first time, will it affect when you throw the dice the second time? No, which means this is independent. Okay, and then remember, pretty much what we're asking here is that the outcome of the roll is not affected by previous roll. Okay. What is the probability of rolling an even number in all three rolls? So here we have probability, roll, even. All right. How many times are we rolling? 3 times. So here we have probability of even number first roll times the probability, I guess I should put a P here, of an even number in the second roll times the probability of an even number in the third roll. So what's the probability of an even number in the first roll? Well, in a 6-sided dice, 2, 4, and 6 are even numbers, so you have 3. Out of how many possibilities? 6. Again, 3 out of 6, because they're independent. Each roll is not affected by the previous. Now, remember, we can simplify these before we multiply. So this is the same as 1/2 times 1/2 times 1/2, which ends up giving you 1. And there you go. Now, if you want to change it to a percent, you can. This would give you 12.5%. Okay? But a lot of times we leave probability as a reduced fraction unless they specifically ask you for a percent. All right, let's look at 10. Consider the following experiment. Drawing a card from a deck of 52 standard playing cards, replacing it in the deck, and drawing another card from the deck. So remember, when we are replacing, means that the amount of cards every time we select is going to be the original 52, which means this is an independent event. Okay? Independent event. So, what is the probability of drawing 2 aces in a row? So, probability 2 aces. So, that means probability first draw ace, probability second draw also an ace. So you may know cards very well, or you may not play cards. So I printed out this from our last section. So these are our cards. So if we're talking about aces, so how many aces do we have? We have 4 aces. Out of how many options? 52. So the first probability is 4 out of 52. And then remember, because it's independent, the second time we draw an ace is still going to be 4 out of 52. Now, it's usually helpful to simplify before you multiply. So if we were to simplify, this becomes 1 over 13 times 1 over 13. And then we can multiply and we get 1 over 69. Okay, because you can divide 4 by both. So you can multiply first and then simplify, or you can simplify first and then multiply. It's your decision. Okay, now this would be approximately 0.59%. Okay, so a very low percent of this event happening. All right, a bag of M&Ms contain 6 red, 5 yellow, and 2 green, 1 blue, and 4 brown. You select an M&M from the bag, eat it, and select another M&M from the bag. Are these events independent or dependent? So think about it. What happens when you selected that first M&M? You ate it, which means you did not replace it. So if you did not replace, means dependent. Okay, and let's make a note of that here. No replacement. Okay. So, what is the probability of drawing 2 yellow M&Ms in a row? So here we have probability, okay, where we have yellow first pick. And then again, yellow, second pick. So let's see. How many total do we have for our first pick? Well, we have, if we add this, 6 plus 5 is 11, 13, 14, 18. So we have 18 M&Ms to choose from. And then how many are yellow? 5. Okay, so the first time you have 5 yellows out of 18 total to choose from. Now for the second time, think about it. How many are left inside the bag? Do you still have 18 M&Ms? No, you only have 17 because you ate one. So now the total is actually 17 M&Ms in the bag. Now, which M&M color did you eat? You ate a yellow. So when you go to select, do you still have 5 yellow M&Ms left in the bag? No, you only have 4. You see? So when it is a dependent event, when it's no replacement, every following event, the fraction will change. Whereas if it's an independent event, every fraction will be the same. All right, let's see if we can simplify before we multiply. So let's see if we can simplify. Nope. So let's multiply across. So let's see, we get 20, and then 18 times 17 is going to give us 306. Well, now we have even numbers, so let's divide by 2. This will give us 10 over 153. And that was our probability. Or if you want to convert it to a percent, that gives you about 6.5%. So not a very high chance of eating 2 yellow M&Ms in a row. Now, what is the probability of drawing a red M&M followed by a green M&M? So let's write it out. So probability, first is red. So red, first pick, times the probability of green, second pick. Okay. So let's look at the red. So we have 18 now, right? We restart the game. So we have 18 M&Ms. And then how many red do we have to choose from? Well, we have 6 red M&Ms, so 6 goes on the top. Now you ate one of those red ones when you go to the second one. So now how many do you have left? 17. And of these 17, how many are green? Well, did we eat any green in the first try? No, which means we still have 2 green M&Ms. And there you go. So can we simplify here? Well, we can divide this by 6. So this ends up becoming 1/3 times 2 over 17. And then 1 times 2 is 2. And then 3 times 17 is 51. This cannot be simplified, so that is our answer. Or if we change it to a percent, you get about 3.9%. All right, what is the probability of drawing 2 blue M&Ms in a row? Okay, so now let's see here. We're going to have probability blue, first pick, times probability of, again, blue, second pick. All right, so restart the game. We have 18 M&Ms still. But now, how many are blue that we have to pick from? Well, we only have 1 blue M&M. Okay? So, you have a chance 1 out of 18 of getting that blue and eating it. So now you ate the blue. Now, when you go to the next one, you only have 17 left. And now how many blue M&Ms are left? Well, none. Because you only had 1 to begin with and you ate it. So are there any blue left in these 17? No, which means you have 0 over 17. So now if we multiply, 1 times 0 is 0, 18 times 17 is 306, and anything divided by 0 is 0, or 0%. What does this mean? Remember, if you get 0%, means it is impossible. And that makes sense. Think about it. If you have a bag of M&Ms and there's only 1 blue M&M, is it possible to eat 2 in a row? No, because you eat the first one and there is no second M&M that is blue to eat. Okay? So if you think about it, right, and you kind of imagine yourself doing the event, it actually makes a lot of sense. Just make sure that you write out each probability, because then that guides you with what fraction to make, okay? Don't skip any steps, because if you skip these steps, you may get confused with what your fraction is and then have a hard time finding the correct answer. All right, let's look at the last one. Consider the following situation: selecting people to serve on a 3-person committee when you have 10 men and you have 10 women. Are the events independent or dependent? Well, does it matter when you're selecting person to person? Yes, because if you select one guy, you cannot select him again, right? You can't put him back into the pool of people. He's already been selected. So this is dependent because we don't have replacement here. We are not replacing the people. Okay? No replacement. So, what is the probability of randomly selecting an all-male 3-person committee from the pool of 10 men and 10 women? So, again, we're going to have probability, right? First pick, male. Then again, second pick, is also male. And then the third pick is again male. So let's see. How many total people do we have to select from? 10 men, 10 women, so 20, so that goes on the bottom. And we want to select a male. So when we first select, we have 10 men out of the 20. All right, now we've selected a man already. So how many left do we have for the 2 positions? Now we only have 19 people. And out of those 19 people, how many are men? Well, we already selected 1 man from this pool, which means there are only 9 left. And a third time to select a male, well, now we've already selected 1 person for the first position, another person for the second position, so now we only have 18 people left in the pool to choose from. And out of these 18, how many are men? Well, we didn't select any women, so all 10 of them, and then the 8 men that are left here. And there you go. So, if we simplify first, you're going to have 1 over 2 times 9 over 19 cannot be simplified. And then 8 over 18 can be simplified by 2. So this becomes 4 over 9. All right, so now if we multiply, we are going to get 1 times 9 times 4, which is 36, over 18 times 19. So let's do that just quickly here. $342. And we can divide this by 9, so that gives us 4 out of 38. All right, which is approximately 10.5%. Okay, so not very likely to get an all-male committee when you have 10 men and 10 women. And that's it.